In the last video, we looked at separation of variables, in the last few videos, I guess. But I'm going to pull your attention back to the overview separation of variables video that I did. Remember, we solved the heat equation, right? We separated the variables of the heat equation, and we were left with this right here. Now, you might be wondering, well, why do I have the second order linear homogeneous ODE circled green? Well, because that's the one that we use for the boundary value problem. We use the second order one for the BVP. So I went ahead and I'm like, well, what boundary conditions could we use? Because for a boundary value problem, it requires boundary conditions to solve. So imagine we have a rod, but we want, remember, U represents temperature. Remember, we defined U of x of t as being this in the separation of variables overview video. So if we have a rod here, this is location 0, this is 0 on the rod, this is length L of the rod, the end of the rod. This as it goes along in x, right? So at the beginning of the rod, the temperature is 0, and at the end of the rod, the temperature is 0, and it's staying at that level. Sorry, my sister is texting me there. Staying at that level. So what was I saying? Yeah, so the temperatures are staying 0. They're 0 temperature on the ends. So those are our boundary conditions. But now, the thing is though, is that we have to rewrite them first. So we can rewrite this by looking at what we defined earlier. Right? So now this is pretty simple. You can just divide by t of t there, right? Because either or, right? So we're not looking at this one at the moment, so just ignore that one. This is what we want right here. And then the other one would be, and you can see from that we would get, right? So that's what we want. Those are the two rewritten boundary conditions. So now for the boundary value problem, we have the second order homogeneous ODE minus lambda x equals 0. And we have the boundary conditions for the beginning and end of the rod. Let me move this down here to the next page. Okay, so to solve a boundary value problem, we're going to look at 3 cases where we have lambda less than 0, lambda equals 0, and lambda greater than 0. So let's look at the first case. So we have, let's start at positive lambda. In order for lambda to be positive, what would make it positive? Think about it for a second. Any squared value would be positive, right? So we can just call it, why does that keep doing that? We can just call it mu squared. Mu just being some arbitrary value, right? No matter what mu you have, lambda is positive. So now, let's plug that into our ODE, and we're left with this, right? We just plugged that in for lambda. So now, think back to ODEs. We just solve the characteristic equation, right? So let me go up here. Remember, to solve characteristic equations, you propose x equals. Now remember, x is in terms of little x. This is big X. is in terms of little x. So this is a little x. Let me put them up here. Little x, x double prime is equal to r e to the r squared e to the r little x. Plug those into the characteristic equation. Oh, sorry, minus. These cancel. And you're left with this, right? So you can solve for r. That leaves us with, so then we can write the general solution for the second order ODE. That's big X is equal to C1 e to the mu little x plus C2 e to the negative mu little x. Right? So now let's look at the boundary conditions. So we had x of 0 equals 0. This is how I like to write it, like this. I like to do brackets. I like to keep everything for the first one in a bracket. So let's look at x of 0 is equal to 0. Now remember, anything with e to the 0 is going to be 1. So we have c1 plus c2 equals 0. So that tells us that c1 is equal to minus c2. So then knowing that, we can rewrite the general solution. Sorry. I wanted to plug that in there. Okay, this is our new general solution. Now let's look at the next boundary condition. X of L equals 0, so we have negative C2 e to the mu L plus C2 e to the negative mu L equals 0. So now this is a little weird. This is a little bit of a new thing here going on. We're going to pull out a C2. E to the, no, let's do this. Let me rewrite it. So I'm going to do it like this. I'm just move these around. Equals 0. So now we're at this point. What do we do? Because you can see before we found that C1 is equal to negative C2. Well, can we solve for C2 here? Well, first of all, what we're going to do is we're going to look at this part. So we know two things here. We know that C2 could be 0. But C2 can also be something else, though. C2 can be any value. It's arbitrary. Right? So really, that part doesn't matter. So we shouldn't really look at this part. We should just ignore C2 for now. But we know that this here has to be 0. So now think about this. What value of mu would make this 0? 0, right? Because if this is 0, then we have 1 minus 1 equals 0. So mu has to be 0. Right? If mu is 0, x is equal to negative C2 plus C2. This is coming from here. That's equal to 0. That means x is equal to 0. That is a trivial answer. We call it trivial because it's equal to 0. Basically. I can't spell. And we don't want this. We want to find an x that is non-trivial. Okay? The eigenvalue can be trivial. So even if mu is 0 here, right? This would be our eigenvalue. It could be 0. Eigenvalues can be 0, but not eigenfunctions. This would be known as the eigenfunction if it were trivial. I mean, not trivial. But unfortunately, not for this one. So let's move on to the next one. Let's look at when lambda is 0. This one's a little easier. You don't have to make up anything for lambda. We just left with, what is it, x double prime equals 0, because lambda is 0. We then solve the characteristic. Correct? We have repeated zeros, so we have repeated roots. I'm using the shortcut for repeated roots, right? It's the shortcut that skips through, what's it called? Reduction of order. If you want to go back to my old ODE videos, check that stuff out. Feel free. This is our current general solution. Let's look at the first boundary condition. This is equal to 0. So let's, if that's x is 0, then we're left with c1 equals 0. That leaves us with x is equal to c2x. Second boundary condition. c2l is equal to 0. Now this one's pretty obvious. That's, you can just divide by L. That C2 is going to be equal to 0 for this one as well. Right, it's always going to be 0 because no matter what length you have, you can say it's like no matter what value for your constant you have, it's always going to be undefined, if that makes sense. Because say the length is, I don't know, 5, right? You can have 5 times a constant. That's just a value, right? And that's just going to be equal to 0. If that makes sense. So that means C2 is going to be 0. So that means you're always going to have some constant that's equal to 0. No matter what length is, or no matter what the length is, right? So C2 is going to be 0. If C2, we know C1 is also 0. So then if C2 is 0, then x is equal to 0. And this is unfortunately a trivial solution. Next case, you can put it right here. What's left? Less than 0? Yeah. If lambda is less than 0, what does it have to equal? Well, kind of like the last one, except we just make a negative, right? The negative not on the inside of the square. So be very careful writing it like this. Make sure it's on the outside of the square. Because no matter what value you have squared, it'll always be positive, but this negative will always make it negative, right? So plug that into the characteristic. Or into the ODE, sorry. It's plus, right? Solve the characteristic. This is going to be complex, right? Because that's mu is negative, mu squared is negative, mu squared is negative. So that's complex. I'm going to use the shortcut for complex general solution for ODEs, second order ODEs. Big X equals C1, e to the 0 is 1, cosine mu x, little x, plus C2 e to the 0 times sine mu little x. First, boundary condition. Sine of 0 is 0. Cosine of 0 is 1. C1 is 0. That tells us we don't need to have all that. Cx is C2 sine of mu x. So this is the possible runner-up for this has to be, because the last two didn't work. So this has to be the eigenfunction, right? This has to be. So now let's look at the next boundary condition just to make sure. We suspect that it is. Eigenfunction. Let's take a look. X of L is equal to C2 sine of mu L equals 0. So now we have to look at this, right? And we have to look at this, and we have to figure out, because we need to figure out what would make this 0, right? Remember, it doesn't matter what C2 is; it's a constant. So we need to figure out what this is, because we can see here that this side, because we want this to equal 0, right? Because the boundary condition is equal to 0, so we want to make this part of it 0. So remember, sine is 0 for what? Any pi, any pi, any 2 pi, 3 pi, 4 pi, 5 pi, and onward. So we can write it like this. We can set this equal to n pi, right? And then, because that's for any n equals 1, 2, 3, and so on, we'll make that 0. We can solve for mu. I'm going to write it like this, because mu is going to have multiple values, right? For every iteration. It's like a series, you know, from n equals whatever to whatever. We have mu1 would be pi over 2. Mu2 would be pi. Mu3 would be 3. Wait, what am I doing? That should not have been over 2. Sorry. Mu would be either pi. Mu2 would be 2 pi. Mu3 would be 3 pi. See what I mean? That's why we denote it with n. So this is, in fact, would give us a value for x. Right? This means we would have a non-trivial x. So that makes us happy, right? Let's look at this. So we want the eigenvalue. Eigenvalue is just our lambda value up here. Okay? Say you picked, for your separation constant, say you picked lambda squared. Well, then you just take the square root of whatever you put on the right hand side. That would be your eigenvalue, right? But we just use straight. That's why I just like to use lambda, because it makes the boundary value problem easier. I think you'd also have to pick something different on the right hand side there, depending on what you pick. So you know that changes that up. But the eigenvalue, we had, you do it for the case that worked. So we had the negative case, which is negative mu squared. So lambda sub n is equal to negative mu sub n squared. So lambda sub n is negative, sorry, this is over L. Right? I forgot to divide by L there. Did I misinterpret my 2 as being an L? I mean my L as being a 2. That's my fault. N pi over L squared. For every n is 1, 2, 3, so on. Now, my eigenfunction. We're going to look back up at our last general solution, which is, we're going to rewrite it as x to the n. Now remember, this c can be anything. So we're going to write it as c sub n times sine of n pi over L times x. For every n, 1, 2, 3, and so on. You can kind of see how we're getting into a series here, right? So, you know, the next step would be to solve for t sub n, because we have x sub n, and then we have to write it out as a general solution, which is a series. So that's when all the fun stuff happens. But Till then, this is a boundary value problem. This is part of solving a PDE, linear PDE, I should say, analytically. I have I think I have 5 more examples on top of this one. There's going to be cases where we have more than one eigenvalue, which means more than one eigenfunction. There's cases where you're going to have sine in your eigenfunction, meaning that you're going to have your mu is going to be different because you want to figure out what would make the inside of cosine 0. I mean, what would make cosine 0, just stuff like that. So there's other little differences that can happen in these problems. So, oh no, wait, this is the overview video. So I have 6 more examples to look at. So we're going to look at all those, and then we'll get into the steps after it. So you can check out those videos, or you can skip them, go to the next part, whatever you want to do. But I'll see you in the next video.